What if, instead of emitting carbon into the atmosphere, you just froze it? Turned it from a gas straight into a solid on the wall of a heat exchanger, melted it into a pressurized liquid, and pumped it underground. No chemicals, no solvents, just physics. That's FrostCC. And in 2024, we ran it for 1,000 hours at a real industrial site in Alabama. The results lined up with what our models predicted, which, as I'll explain, is actually the most interesting part. Quick context. There are thousands of industrial point sources out there. Cement plants, steel mills, refineries, gas power, coal. They're going to keep emitting CO₂ for decades. Today's go-to capture method is amine scrubbing. The process is to spray a chemical solvent through flue gas. Then that solvent grabs the carbon dioxide. Next, they heat it to release the CO₂. Repeat, it works. But amines can corrode equipment, evaporate, degrade, and need a lot of heat to regenerate. They also don't like nitric oxide or sulfur oxides. So you end up bolting on extra scrubbers and a compression train just to make the whole thing work. For one job, you need 3 technologies. And when you add up the real fully loaded costs that National Energy Technology Laboratory published, the headline price tag gets a lot bigger. We are FrostCarbon, based in Arvada, Colorado. Our approach is different. We compress, cool, and expand the flue gas until the carbon dioxide hits the right temperature and pressure to desublimate. It skips the liquid phase and freezes straight onto the heat exchanger as frost. The cleaned exhaust comes out with sharply reduced nitric oxide and sulfur oxides. Then we warm the exchanger, the frost melts into pressurized liquid CO₂ ready for the pipeline. Then the cold exhaust loops back as the system's own refrigerant. No external cryogenic fluid, no solvents, just electricity. Here's how the 2024 pilot at the National Carbon Capture Center went. 7 phases. Over 1,000 hours of continuous capture. Peak efficiency hit 99%, with a 92% cumulative average across the campaign. Product purity was 99.97%. The system advanced from Technology Readiness Level 5 to TRL 6. Basically from works in a lab to works at real industrial facility. And the heat exchangers showed 0 degradation, because there's nothing to degrade, they just freeze and melt. But here's the part I actually want to talk about, the models. Before the pilot, our physics models were tuned on a small 10-ton per year lab rig. The NCCC pilot scaled the heat exchangers up roughly 100 times. If the physics didn't hold at that jump, every future design would be guesswork. Instead, outlet temperatures matched within 5 Kelvin, capture efficiency matched within 2 percentage points, across more than 100 frosting cycles on 4 heat exchangers. That matters because scaling thermal systems is full of surprises. Ambient heat losses, expander efficiency, recuperative cooling all change as you go bigger. Most of those changes actually work in our favor at larger scale, but only if the model can predict them. FrostCC's did. We took it further this year. At the 2026 American Institute of Chemical Engineers Spring Meeting, we presented physics-informed AI surrogates that were trained on our validated physics models. These AI surrogates were fast enough to run thousands of design scenarios in minutes instead of days. Same physics, more speed. And the commercial design is modular. FrostCC is factory-built, identical skid trains that ship to site and stack. If you want 1 million tons a year, just add trains. If one train is down for maintenance, spares come online. This works because there is very limited custom engineering at the core process level. As an industry, carbon capture's flashier solutions tend to get the headlines. FrostCC is cold pipes, phase diagrams, 1,000 hours of the same experiment, and a model that keeps matching the data. If you want to follow what's next, our commercial demo, the AI accelerated design work, and whatever the next scale-up teaches us, please subscribe. That's what this channel's for.